Thank you. Good morning, everyone. So today's lecture is going to be all about semantic effective field theory. So the beginning of my lecture, the first part of it, is pretty much textbook material. Some of the notation, some of the emphasis is a little bit different because I take a slightly different point of view with an eye towards developing this framework for massive quarks, heavy quarks, and in the literature, semantics original work, and a lot of the work done in the 80s and 90s on improved actions was focused on light quark actions, and I'll talk a little bit about that. So it's this should be familiar if you've studied this in a course or in textbooks. So it might be a reminder in the beginning, and then we'll delve into some details that are not in textbooks, but some of these things are in lecture notes, summer school lecture notes, and well known in the literature. And at the end of my today's lecture, I'll have some slides to loop back to some of the results that I showed you. And so we'll make the connection to this framework and the results at the end. Hopefully I'll get there. Okay. So of course, whenever we have an effective field theory, we start with a separation of scales, and the scale separation is clear in lattice QCD. We have the short distance, smaller than lattice spacing in infrared. That's driven by the hadronic physics. And so the semantic EFT gives us a prescription for how to analyze discretization effects in an EFT description, whereby the semantic Lagrangian, the EFT Lagrangian, is written in terms of continuum fields. So everything on the right-hand side of this equation here, the right-hand side is written in terms of continuum fields and renormalized couplings. And the left-hand side is, of course, the lattice theory with the bare couplings, etc. And this notation here, this equal with a dot, this was introduced by Andreas Kronfeld, my longtime collaborator, and it means not equivalence of the Lagrangians, it means equivalence of on-shell quantities, particularly that are obtained with each Lagrangian formulation. So if I compute physical quantities, if I compute masses, matrix elements, all the things that we are after, then it is the physical quantities that I compute on the lattice, and then expressing them in terms of my semantic EFT, that is what this symbol describes. So the shorthand notation is I'm going to be writing these things in terms of the Lagrangians, but then you still have work to do to work out the corresponding expressions for the on-shell matrix elements, masses, and so on. And the reason why it works this way is because if I've developed these expressions at the Lagrangian level, then the statement is that these are these statements then hold for any physical quantity that I compute, and I match this way. And I don't have to get the details, of course, for any particular quantity, but I don't have to rederive it for every quantity. So that's the point of this.
The hadronic metric element could
So I will be focusing, in principle, yes, we can extend this to off-shell quantities, but I will be focusing my discussion on on-shell quantities. I'll have a little bit to say about off-shell tomorrow, but, so for now, keep on-shell in mind. And yes, in principle, you can, but that becomes harder, and the statements that I make don't all hold in that case. Okay. All right, so let's see. So these are the parameters then of the lattice Lagrangian, of the lattice field theory. So the sub naught, that's common notation, and then there will be some coefficients that are coefficients of higher dimensional operators in the lattice Lagrangian, not specified yet, because right now I'm writing things for a generic lattice Lagrangian. So these are the parameters of the lattice Lagrangian, and the renormalized couplings will depend on all the parameters in the theory, including the matching conditions and the matching scale. Okay. Then the gist of this is that in my description of discretization effects, I'm matching my lattice theory to the continuum QCD theory plus corrections. So all of the discretization effects live in here, and then this whole framework works if this is small. And we'll talk about what small means, and we'll talk about how this is not small anymore, at least initially, naively, when the quark masses become large. Okay, so discretization effects live in L sub I. All right, so generically, then L sub I contains operators. Let me write this down. So generically, L sub I will contain an infinite tower of operators that are of dimension higher than 4, with some coefficient functions, k sub n's. And again, these are renormalized operators. The coefficient functions are, again, functions of the same parameters as before, and the operators, matrix elements of these operators, expectation values, etc., will scale like some positive power of lambda, where lambda is the typical momentum in the system. And so here's one thing where on-shellness is already implied, because when we deal with an on-shell system, we can talk about typical momenta. When we deal with off-shell systems, we can't talk about that in general. But okay, so these matrix elements encode then the long distance effects, and these are then balanced by corresponding operators, corresponding powers of A. So this is how we get a description of A lambda to some power of discretization effects that scale with some positive power of the lattice spacing. And if A is small enough, so if A times lambda is smaller than 1, then L sub I is basically a perturbation And we can treat it as such, inserting it into the correlation functions, okay. And coming back to the discussion of on-shell versus off-shell, so there's a whole series of papers that basically discussed that it is okay, it is enough to consider, on-shell improvement to then improve all on-shell quantities. And this simplifies the discussion, because if I limit the Lagrangian, even at the, if I limit the possible space of operators to only consider on-shell quantities, then this reduces the space of operators that I need to include in my Lagrangian, so I have fewer operators, and the matching calculations are simpler. So the operations that to look at on-shell improvements, we can use equations of motion, we can use field rotations, so-called spectrum conserving rotations. So with, in the path integral language, to illuminate the redundant operators that can be dropped from the semantic Lagrangian. Okay, so I'll show some examples of using equations of motion because that's a little bit more intuitive, but the references that are in my notes, which I will share with you, these are handwritten notes, but I try to write cleanly, and I'll share these notes with you at the end of the lecture, and there's references with links that take you to the papers that you can look at them yourselves. Okay, so are there any questions? I'm hoping this is not completely unfamiliar. So let me start, again, keeping things familiar. Let me start with the Wilson gauge action to kind of sketch how this works. And has everybody done this calculation before? Wilson gauge action, write down the Wilson gauge action, and do this small lattice spacing expansion to show, okay, let me sketch it out. So the Wilson gauge action can be written in terms of the plaquette operator, which in my notation becomes 1/3 real trace of the link field, and the link field is defined as usual as the path-ordered exponential u mu of x, u nu of x plus a mu hat, u mu dagger of x plus a nu hat, and then we have u mu dagger of x. So that's my plaquette. That's a little thing going around like this. And the gauge action is built out of the plaquettes. So we have the Wilson Lagrangian. There's my coupling in front, summing over nu greater than mu, 1 minus p mu nu of x. And then the action is the sum over that. And beta is 6 over g squared, as usual. And if I expand this, then you can show that this becomes 1 over 2 g naught squared, trace of g mu nu squared. And then you work out the next term. You get a squared over 24, trace of g mu nu, d mu squared, d nu squared, g mu nu. And of course, we're now in Euclidean space, so there's no upstairs and downstairs. It's all either up or down, doesn't really matter. So this analysis then shows us that the Wilson-Gage action has discretization errors of order a squared. And so all terms in the semantic Lagrangian, all terms in here, start with dimension 6 operators. There are no dimension 5 operators in the pure gauge case. And of course, those are the leading order terms. And then this description suggests that you can add dimension 6 gauge operators that are built, for example, from a plaquette like that. So work this out. And so if I'm going to call this R mu nu, and I'm going to take a third real trace of this thing, then I can construct an improved action, an improved gauge action, like so. So that's one example. And then if you expand this out again, you can easily show that, easily with a little bit of algebra, show that this improved action has no a squared terms. So the L sub I with this improved action, start at dimension 8, not 6. So this is, of course, all classical or tree level, and this can be extended and has been extended. One-loop corrections were computed already in 1985. This is an old story that goes back to the 1980s, and it is always worth revisiting that because it is really the backbone of modern lattice QCD simulations. Without improved actions, without this knowledge, we would still have the computers we have. We wouldn't have the results we have. Okay. Are there any questions so far? Yeah.
So this R mu nu that you have defined,
Mm-hmm.
it is again a plaquette but a rectangular one.
Yes. So this is mu, this is nu in my notation here, yes.
But what I'm trying to understand is that in this semantic improvement, what you mentioned that we are supposed to add a higher dimensional term.
Yes.
But how is that a higher dimensional term, this R mu nu, that I did not understand?
Okay. So you can see how this term includes more link fields, right? Mm-hmm. And, roughly speaking, then, this corresponds to, or it contains now dimension 6 operator as well as dimension 4 operators. So, so we're building, so basically you can think of this as a discretization of this continuum term. Okay, so
And one last question.
yeah, so let me just this is an exercise that you could do this afternoon or tomorrow if you wanted to. And this is a further exercise that you could do. So I haven't written down the definition of the link field in terms of the underlying, gauge fields, but that's in my notes. And so you can work this out classically. Okay, so I'm kind of showing the results and not the steps, taking this as an exercise. As I said, this is pretty much in all of the textbooks these days.
But one last
Yeah.
thing is that, so we add a term with our Lagrangian. So I did not understand that from Lagrangian we construct the equation of motion. Adding a term will affect the equation of motion, and that will have consequences.
Okay, so it is not so much that we add terms, it is, and I'm showing this here in an example, the construction, the construction is, we start with a lattice field theory, right? So we start with, say, the Wilson-Plaquette action that I've written down here. And then we say that physical quantities, on-shell quantities computed with this action can be described by an action that contains the continuum QCD action plus terms, operators of higher dimension, all written within, as expectation values of my continuum fields. Okay, so I'm not adding anything. I'm figuring out which are the terms that go in here to match the lattice theory to a continuum field theory that starts with a QCD, in this case with a Young-Mills Lagrangian, and what are the higher order terms that are in my semantic EFT that provide a description of my discretized action.
So at some point, if I set the lattice spacing to be 0, then this term will not have any effect.
That is correct.
Okay.
And so that is what is shown explicitly, somewhat explicitly here. So this, of course, means that these coefficients don't contain any power law divergent terms that would destroy this. So this is part of what you need to show or work out, that these coefficients, of course, also stay finite, so they don't destroy the scaling. We're not deriving this. I'm showing you the results. I'm showing you the framework, and this is very generic. It's written very generically, and it always holds, at least for the cases that we'll study. Okay. So it is exactly right. When you look at this, this is a Lagrangian of higher dimensional operators that needs to be balanced by dimensionful coefficient in order for this to be a Lagrangian that gives me a dimensionless action. That's always the case. So that's the same principle that you have whenever you write down an EFT that is an expansion in terms of higher dimensional operators. There's always a dimensionful parameter that balances it, and whether the EFT is chiral perturbation theory or any other EFT or the standard model EFT, it's the same principle. And here the EFT looks different from what we're used to in the continuum. But by construction, then when I take the continuum limit, then Li, so as A goes to 0, L sub I, or anything that contains the L sub i's, is also forced to 0. And in that sense, in that sense, then if I take my lattice spacing small enough, that is when the L sub i's become a small perturbation. What is interesting about this framework is that it tells us explicitly what the leading discretization errors are. The lattice gauge action, the Wilson gauge action, doesn't have discretization errors that start at order A. So I haven't, you can show this by doing this calculation, right? And so there are no, that means that in the corresponding semantic EFT, there are no dimension 5 operators that arise, it's always even dimension. You get dimension 6, you get dimension 8, etc. And so, of course, this is only worked out at the tree level. And if I use this action here, then I know that this action doesn't have any terms. There are no order A squared terms, discretization terms in this action. However, if I do the matching only at tree level, I will still have terms that go like alpha S A squared, A lambda squared, right? So I can take this matching further by working out, working this out through one loop. And again, there's a reference. This was done in 1985 to remove the leading alpha S terms. And of course, you can try to work out matching conditions to do this non-perturbatively to remove at all orders all A squared effects. But this is in general not really needed for the gauge action though. Okay? Okay. So these are all good questions. Are there more questions about this? Good. So I didn't want to spend too much time on the gauge.
The alpha S in the leading order correction, at which scale should it be measured? Because in principle, alpha S at low energy is large, but at which scale is that?
So this would generically be at the cutoff scale.
Okay. So
I mean, you want to set this up in a good way. Okay, I think I will leave that there, and I'll erase this. As I said, you don't need to take notes because all of this is in my notes, and it might be more legible than what's on the blackboard. Okay, so. Let's go to another Wilson, oldie but goodie, the Wilson fermion action, which we all know and love. So we have a mass term, we have the derivative term, and the covariant derivative. I'll write down in a minute, but it's not a surprise. And then the Wilson action has this Laplace term as well. And usually in numerical simulations, R is simply set to 1. And let me just write down once the covariant derivative. So I'm writing it, and it is usually written as in a symmetric way, spanning 2 lattice spacings with the gauge fields, connecting this so that I still have the same gauge invariance. So the gauge symmetry of my lattice action is the same as the continuum gauge symmetry. That was the thing that I didn't write down, is how to write the gauge fields in terms of the link fields, the plaquettes. Any closed Wilson loop is gauge invariant, and so we have exact, explicit gauge invariance in the lattice theory. What we don't have is continuum Lorentz invariance or Poincaré invariance. Those, of course, are disappear as I take the lattice spacing to 0 limit, and Jeremy was talking about the effects on the spectrum as a result of not having rotational invariance, for example. So we won't really talk about that, but the fact that we maintain explicit exact gauge invariance is very important. Okay, so we have the Wilson term, which is written like this. Okay, so this is a second order derivative term. And so the Wilson term is dimension 5. And of course, then needs to be balanced with lattice spacing in front. And you guys know the story about why Wilson added this term to the action. What's that story? The doubling problem. Okay, so that's a lovely story. That's again in all of the textbooks. So if you haven't worked this out yourselves yet, then I invite you to work out for the naive lattice action. So the simplest thing you can do, and let me just not worry about example or exercise. I'm going to drop the mass term for now. So then you just have the fermion Lagrangian. This is just the naive derivative, as written here. And do this in at tree level. You work out that the propagator for the naive action takes this form. And the fact that you have, 2 zeros on the Brillouin zone, then this gives you 16 poles and 16 particles. And in contrast, the free Wilson propagator, so I'm going to call this DWP, takes this form. So just working this out from the action as shown. So of course you get the naive propagator, and then you have an additional term like so. And we'll talk about this a little bit more later on. It's straightforward to show that this additional term lifts the doublers, and so you're left with one physical degree of freedom. And the cost of removing the doublers in this way is that we've added dimension 5 operator on the lattice side, and that directly translates. This delta becomes a d squared, so that directly translates into my semantic formulation. In the first operator here is a dimension 5 operator. That is the semantic EFT of the Wilson fermion action. And so it means that the Wilson term adds order A discretization errors. So if you have not ever done this yourself explicitly, especially if you work with Wilson or improved Wilson fermions in your simulations, if you do any of this analysis, I think it is required that you do this yourselves, and you can do this, of course, at your leisure. So the mass term that is acquired here, is goes like the inverse lattice spacing, and is hence lifted to infinity in the continuum limit. Okay, so let me okay. disintegrating here in front of your eyes. So I think I do want to work out the semantic EFT for the Wilson fermion action, or at least write it down. You guys can follow the algebra later on. So the Wilson semantic EFT starts with, of course, okay, I'll just write this as d slash psi, and then I have the L sub I. And as we said, it starts at dimension 5. So what are the possible dimension 5 operators? They are these are the, I have this dimension 5 operator, and then I have this dimension 5 operator as well, which is d slash squared. And the two operators are not independent from one another. I can write O5 prime as psi bar f d squared psi f minus 1/2 O5. So basically, I can generate the O5 prime, the d slash squared operators, via field transformation, field redefinition. So if I take psi sub f and, or just, and rotate them by, like this, the psi bars get rotated like this. Then such a field rotation generates, you expand it back, it generates, this operator here. So that means that O5 prime is redundant. You can also do this analysis looking at the equations of motion. And so you can work out that the semantic Lagrangian starts the leading order a term, the leading order dimension 5 term in the semantic Lagrangian can be written in terms of O5. I don't need the O5 prime. I only need one dimension 5 operator to describe the Wilson gauge action, plus higher dimension operators that now, of course, start at dimension greater than 5. And I have an infinite tower of these things. So these give me then a description of a squared and higher order terms. And all of this is, of course, done at tree level. So just like before, which I have already raised for the Wilson gauge action, we identified the leading order discretization terms as a squared terms. We found in the semantic EFT what is the leading a squared term, what it looks like, and then you can add a rectangle operator to the gauge action to have the improved gauge action with coefficients that have to be adjusted so that when I do the expansion, in the semantic EFT, the leading a squared term, the leading dimension 6 operators, the coefficient in front of it is 0. So we want to now add an improvement term to the Wilson action so that when we work out the semantic EFT, so that this term goes to 0. Okay, so that's the procedure for working out the improved action. And of course, we're not really, I'm showing this, I'm writing this at the level of the Lagrangians, but remember, the analysis is done for on-shell quantities. But I don't have to do this for every on-shell quantity, repeat this. I can do this for one on-shell quantity that's convenient for me to study, and then I know that I have that improvement with those coefficients for every on-shell quantity. So you can then check it for other things or do this in other ways. So, convenient on-shell quantities, when I work in, a perturbative expansion, when I sort of do tree-level calculations, it's just the quark propagator and the pole and the residue of it. That's a convenient on-shell quantity. Of course, if I'm doing this non-perturbatively, then my on-shell quantities are hadron masses and matrix elements, etc. Right? Okay. So in perturbation theory, I can use external states of quarks and gluons. I can use, I can look at the vertices in this way. And of course, when I do this non-perturbatively, then I need to look at the hadronic external states. Okay, are there any questions?
The d square, should it be d slash square? In 5 prime?
No,
No?
no. O5 prime is this. And then O5 prime is related to O5 like so. Yeah.
Is there a reason for picking 05 instead of 05 prime? I mean, is there any advantage up here?
Yes, of course you could, if you picked O5 prime, really what you would be picking is this. And this is convenient because, look at this here. I'm not needing to add higher order derivatives. What is this? This is the F mu nu, the G mu nu term, which I can represent also. On the lattice, this gives me the Clover term. So this is convenient because it's psi bar psi sandwiched with the F mu nu term, which I can then the discretized version of this is the famous clover leaf, right? And so implementing this is easier than implementing an operator that has higher order derivatives in it that can give rise to some other complications. Okay, so I don't want to, I start with a Wilson gauge action. I already have this term in, a discretized version of this term in here. And then I add this term, and this then gives me the Clover action, what is known as the Clover action, also known as the Shaikos-Sulami-Volat action. Okay. So you anticipated what I was going to say next. How are we doing in time? Okay. You have already memorized all of this. I'm going to leave this up. Okay, so we're picking this one here, and we use this one here. So the Shaikos-Sulami-Volat action, or Lagrangian, starts with a Wilson fermion action, and then we have this is here, where this is a lattice version of f mu nu that I've already indicated over there, and I won't write out, though it's been written out. And of course, you write the different combinations out, and this is all in the literature. So then the name of the game is that we adjust the coefficient CSW to remove order A errors from on-shell quantities, and for depending on if I got all the normalizations correctly, in the case of light quark actions, this can be set to 1 at tree level to remove the leading order A terms. Okay. So let me see. Let's do this. So here's another exercise, or an invitation if you want, if you haven't done this before. It turns out that when you work out the external states and in the lattice fermions and continuum fermions, that for the states, discretization errors start at order A squared. So to kind of do the improvement, to work out the improvement conditions, the simplest thing I can do is just look at the vertex to obtain the improvement conditions, because that's the only one that is affected at order A. Of course, underneath that statement, is a longer calculation that I'm not going through. Again, this is material that is well known. So your exercises would be to A, derive the naive vertex in momentum space. So for the naive action, and you should see that you get minus I G naught TA gamma mu cosine of 1/2 P plus P prime mu A, and you can then do the same thing for the Wilson one. So work out that vertex. I think all my mu's are downstairs. And you get cosine of 1/2 P plus P prime mu A, and you get the sign like so. Again, if you've never done this, now is your chance. And if you've done this before, then you can check your notes against my notes and see that it all agrees. And of course, the improved action will have the same vertex as the Wilson. And now there's an additional term. Okay, so one thing that you learn very quickly is that the expressions become annoying to write down. And there's ample opportunity for me to mess up signs, etc. But basically now what you have to do is just, match this to the continuum vertex, right? And we all know what the continuum vertex is. And it's pretty clear that the naive action has this, the naive vertex starts at a squared. Then you can work out how you get order A terms here. And then you can work out what value CSW has to take to cancel the order A terms. And as I said, you imagine sandwiching this in a matrix elements of external quark states, and you've worked out that the external quark states, start at a squared. So when you work the whole on-shell quantity out, then you get that, the only thing that matters is looking at the vertex function to have on-shell improvement. So none of this wouldn't work if I hadn't worked out the external states, external quark states already. So, this is still an on-shell program. We're not doing off-shell improvement here. Okay. Of course, you can, what you want to do is work out the, use the Gordon identity. Again, of course, because we're looking at on-shell stuff here in order to simplify the expressions. So that's a hint if you attempt this exercise. Okay, now in my notes, there's also going to be a discussion. I'm running out of time, so I'm not going to go through that. There's also a discussion of what happens with external currents, because in the end, we're often interested in weak matrix elements. So we have our action, we have our Wilson action or improved Wilson action, the Shaikh-Islami-Woolard action or some other action. And when we want to compute matrix elements of weak decay operators, those are described by adding an external current. So that's not part of my QCD action. That's coming from the electroweak sector. And those external current operators, I need to go through the same improvement program as, for the action itself. So with this program here, I have guaranteed improvement of all QCD quantities, all spectral quantities, quark scattering, etc. If I want to have weak matrix elements improved, then I need to take the right value for CSW, and I also need to consider currents, axial vector currents. I need to work out those on-shell improvement conditions, and I will have improvement coefficients for those that I have to set up in a similar vein as this. And again, with the, with what I already said about the external quark states, starting at a squared, I really only have to look at the currents and imagine I'm sandwiching them between quark states in order to work out the improvement conditions, and remember that I'm still doing on-shell improvement. Okay. So I'm going to skip that, I think. Yes, I think I'm going to skip that, but it's in my notes, and if you guys have questions, you can still find me. Okay. Because I want to talk about heavy quarks, that was the whole point of this. All right. Yeah, let me start here. So just actually, let me add one note. In the traditional semantic papers and the first improvement papers, the they were worked out, basically at 0 quark mass, and then mass terms were added as higher dimensional operators. Or you can keep the mass terms in the description the way that I did right away. And especially when you work this out for the currents, you can see that you get the same description either way, because in the end you can expand in small masses. So what we've done so far, all of our work so far, is assuming that m times a is small compared to 1. So I don't have, of course, here I've kept this mass term here, but I've pretty much ignored it. When I worked out the propagator, I've set it to 0. But so far, all of my discussion has focused on essentially the massless limit, or when ma is smaller than 1. So m might also be smaller than the typical momentum scale. So, mass terms are basically a small perturbation on top of the semantic improvement program, and I can accommodate masses, that are commensurate with lambda. But if I want to consider heavy quark masses, so when I want to consider that m times a is not negligibly small compared to 1, so this now becomes heavy quark physics. So this is relevant for charm and beauty or bottom quarks. I think bottom is the American notation. Okay. So, of course, for charm quarks, with typically available lattice spacings these days, we have, m times a is, around 0.2, 0.3. It's still quite small. But for charm quarks, we have definitely m charm is larger than the typical momentum scale, which we think of as being lambda QCD. So for charm quarks, mass effects are not a small perturbation, but must be treated at the same level as lambda. And again, you can still expand if you want, but you might want to expand more carefully. So what we're going to look at now is if we don't expand in masses, if we just keep the whole mass dependence. And the first thing is to see what goes wrong, right? Something's going to go wrong. Why? Because when m times a is of order 1, when m times a is of order 1, as I take of course I can always brute force it and go to lattice spacings that I don't have access to. But when m times a is of order 1 at, the finest lattice spacings I have in my simulation, then, any power of ma is large. So I always have large, no matter what level of improvement I've achieved. I've removed order a terms. I've removed order a squared terms. That's hard. I always have large discretization errors that I don't have good control over. But the question is also, how do I see this? How do I see this in the semantic EFT? Where does the semantic EFT actually break down? What goes wrong? How is the semantic EFT modified by mass? So that's the thing that's not in textbooks. Okay, but it is in a bunch of lectures, lecture notes that are referenced in my notes. So let me start with a fun exercise. So here's the exercise. So work out the quark propagator as a function of Euclidean time and 3 momentum. So it's this object here. So we have psi of p prime t prime psi of pt. And psi of pt is just the Fourier transform of psi of x. And you can write this as, I'm just writing it all explicitly out. And this is the thing that we want to find, the quark propagator as a function of Euclidean time and 3 momentum. And this object can be obtained from the now erased quark propagators that I worked out before. So from the d tiddles, like so. So you have those expressions already in the notes, and you either derive them yourselves or use the notes and trust that my notes are correct, right? So you plug in here any of the propagators that we've worked out in momentum space for the naive action, for the Wilson action, improved Wilson action, any of these guys. And it is actually instructive. It gives you a different view also of the doubling problem to plug in the naive propagator here and to use the residue theorem to work out the poles. It's actually easier to start with a Wilson action in this case because you only have one pole. And so working through the integral, you're gonna, so I'm giving you the steps, but I think you've done this before, to use the residue theorem to work out this propagator. And what you find in the end, for any given propagator, you're going to get an expression that looks like this. So for the Wilson case, for the Wilson case, you're going to get an expression that looks like this. There is a wave function normalization that, in the lattice case, will depend on p. And then there is an exponential fall off that goes like e to the minus t absolute value t, and some god-awful other coefficient that we care a little bit less about. And then you're going to get a condition on E versus P and M naught, and that is the energy momentum relationship that tells you how what the rest mass is in terms of M naught and what the how the energy momentum relationship is distorted by discretization effects. Okay, so this is a really cool exercise to do. If you haven't done this before, I highly recommend working through this. I find it very satisfying. And then once you work out the energy momentum relationship, you get some expression cosh E in terms of M naught and for the Wilson action, P squared, et cetera, et cetera, et cetera. Then you can expand in AP, in powers of AP. You might want to drop the powers of A for a while and then reintroduce them, so you expand in small powers of P. Why can we do that? Why is it okay to expand in small powers of 3 momentum? We're not expanding in M naught. M naught is a free parameter. M can be anything. We're not doing a small MA expansion, but we're still doing our semantic EFT. We're still having an eye towards the continuum limit. So P is my typical momentum, so I can still expand in small AP in order to understand the discretization effects and then look at the what powers of A come in and look at the energy momentum relationship. So then you get, you define M1 typically as the rest energy. So you work out an energy momentum relationship and define the rest mass as the energy at 3 momentum equal to 0. And then we define something that we call the kinetic mass, which is the slope of E versus p squared, again taken at p equals 0. And of course, in the continuum, what you expect to find is that E squared equals m squared plus p squared, continue in the Euclidean space, right? And what happens is that for the Wilson action, you will find well, actually, generically, you will find that E squared equals m1 squared plus square root of m1 over m2 times p squared. So the kinetic term, the energy momentum relationship is distorted by m1 over m2 not being equal to 1. So if m1 is equal to m2, then we have the usual relativistic energy momentum relation, and then we'll have terms that go like ap to the 4th order, right? Sorry, that go like p to the 4 with a squared coefficient in front. So if m1 is not equal to m2, then we have discretization errors in here. And if m1 not being equal to m2 is large, then you can see that the energy momentum relationship is distorted. Okay.
You want to have m1 over m2 maybe then in this derivative. In the derivative,
Yes.
the definition of m2, perhaps m1 over m2 on the left-hand side. Or even the square root of that, or just to match what you wrote on the other blackboard.
No, I think this is correct.
But here, if I take the derivative,
Okay, so maybe no, let me get back to you on that.
okay. Yeah.
So you have to add, yes, I think the square, sorry, I anticipated the square root for later on. I think you are right. I'm going to check my notes later on because I'm not even good at reading my notes. So if you go through this, what you find is that m1 over m2 goes like 1 minus 2/3 m1 squared, and plus higher order terms. So again, this is expanding it in powers of am naught. So the first correction terms of order m1 squared. For the Wilson action, m1 looks like log of 1 plus m naught. So this is an a squared effect, but of course an a squared effect that is potentially large. And happily, however, this goes to 1 when I take the continuum limit as it must, as it should. So nothing that we did before where we assumed MA is small or we expand in MA, all of that is completely consistent with this. Okay, so there's more results in my notes. I'll give you explicit expression for M1, for M2 as a function of M0, and also of Z2. And what we find is that Z2, where are we? Is not just normalization, but it depends on not p squared, but on p. And again, if you expand this in small p, you get 1 over 1 plus m0 plus terms that vanish at order p squared. Of course, in the continuum, this should be a function of p squared, not p vector, but we have this on the lattice. So what we find is that the normalization of the fields is also affected by the mass. And if I want to have a canonically normalized field and want to have, heavy quark states that are normalized correctly, then I need to, construct current operators with a properly normalized fermion field. And these factors here are known as e to the, this becomes e to the minus m. And again, in the limit when m times a is not small, this becomes a significant correction. And it can distort the continuum limit if you think that you can just, forget about the normalization. Okay, so basically, when the mass becomes large, they are now illuminated, but prior to this, hidden discretization effects that you can always brute force by making the lattice spacing small enough. But if the lattice spacing is not small enough and you're pushing your simulation towards large masses, then you might extrapolate to the wrong place because you haven't taken these terms into account. So what we need to do is we need to work out the semantic EFT with, in the presence of large masses. Okay, there was a question, yeah.
So we assume in this case that P is small, right?
Yes, P is always small.
So P is small in comparison to lambda then, right?
No, P is lambda. P is small in comparison to the lattice spacing. So A times P is small.
Okay.
So we still have, we still want to construct a semantic EFT. We still have a small parameter. A times lambda is still small, but now we have, so what we have, right, to put it in the language of EFTs, what we have is when the mass is large, we have an additional scale that we need to take into account. Okay, so in addition to the momentum scale or the, that is treated with a semantic EFT, we now have a large mass, and we need to take that scale properly into account. So we don't want to assume that the mass is small in lattice units. So we have the lattice spacing scale, we have the momentum scale. We assume that momentum scales are small in lattice units, but we don't assume that the mass scale is small in lattice units. We don't want to throw everything out. So, okay. So one more thing that I wanted to note. We're talking about heavy quarks here. And here I have the relativistic energy momentum relation. If I go to the non-relativistic limit, so if I just expand now in p squared over m, then the non-relativistic energy momentum relation becomes m1 plus p squared over 2m2 plus higher order terms. And this already suggests a solution. So there's a lot that we learn from this exercise. This already suggests a solution that I've already alluded to in the previous lecture. When we look at heavy quark systems, whether it's HQET or NRQCD, and you study the Lagrangian, you might notice that the leading term in the continuum literature doesn't have a rest mass, because the rest mass is unimportant. The dynamics is, is given by, by what is in this framework higher order terms. So I need, if I want to describe a heavy quark correctly, I need to make sure that the kinetic term is correctly normalized. If the rest mass is incorrect, that's an trivial shift. And then actually, this has been worked out also in the lattice case that rest mass effects are basically trivial. And so one quick way in which I can avoid this large error is by, instead of taking the rest mass as the pole mass, as a physical mass of my quark, I tune the quark mass m0 until m2 takes on the physical value that I want. And with that, you've avoided an important source of systematic error right away. So that's a prescription that works. We've seen that it works also through one loop order and perturbation theory, and that is the first step in a more systematic approach towards using improved Wilson fermions for heavy quark physics. That's known as the Fermilab formulation. So that's the first thing you need to do, and then the second thing you would do, you would also adjust the normalization of your fields in this way. Take this normalization into account, and you've already removed two important sources of error. And then what I will show, what I don't have time to show, unfortunately, I'm going to have to see what I do with my lecture tomorrow. In any case, what you can show is that there is a systematic program that starts from a non-relativistic or heavy quark effective theory point of view and improves the lattice action by matching, instead of matching to QCD, matching to first HQET or NRQCD and then back to the continuum. And I'll mention this. Okay. Good. So maybe I started too slowly. Now, if you take the insights from from this analysis, and they suggest solutions right away. But if you just go ahead with a usual semantic EFT and work out what the L sub I look like in the presence of large mass terms, then the question is, how does the semantic EFT get modified? And the L sub i's will have some terms in it that look like this. Starts with n equals 3, a sub n, kn, some 0 to 3, psi bar, gamma mu, d mu to the n psi. So generically, you're going to have higher order terms in my semantic EFT for any fermion action with any mass that, look like this. These are compatible with all the symmetries, etc. So these are generic. Now, if we do our work on illuminating the redundant operators and removing redundant operators, then we can use the equations of motion. And in this case, as I'll show in a minute, the trouble arises from higher order operators that are time derivatives, because the time derivatives will be associated with mass by the equation of motion. So the equation of motion is just this, right? And so I can apply the equation of motion here to replace all terms that come with d naught with the spatial derivative plus m. What this is telling us is that this is not small if m is not small, right? The derivative term, basically it means that gamma naught d naught psi is scales like m naught psi. The derivatives, spatial derivatives, are still small because remember, AP or A lambda is small, and the derivative will scale like the 3 momentum. So this is not small. So this means that I have these higher order terms in my semantic EFT that are not small. So the L sub I now is not small in that sense that these operators and coefficients are small perturbations. They're still small if A is small enough that A times M is small. That still all works. But if A times M is large, then these are large. So now I have large discretization terms in here. And the result of doing this, applying this equation of motion, n times, you will get something like a to the n gamma dot d plus m to the nth power. So doing this n times, then you're going to get commutators, etc., of d naught and di that are field strengths, which are small. So in the end, you get an expression that looks like this, that you expand as ma to the n minus L, a to the L, psi bar, gamma dot d to the L psi. And you can see that, if L is equal to 0, if L is equal to 0, then you just get terms that modify the coefficient of psi bar psi. If L is equal to 1, you get terms that modify gamma dot d. So what I've sketched out here is using, on shell, studying the redundancies by using the equations of motions to rewrite the large terms in terms of small terms operators with coefficients that are now mass dependent, where the largeness of the terms is explicitly illuminated. And what comes out of this, so of course I haven't derived anything, I've just sketched it.
What is L?
This is just expanding this.
Okay. Summation. Okay.
Yeah. Just looking at all the terms that are in here, okay. So what comes out is this. And now, Harvey, we have a square root. Okay. Now these guys are small. because they only contain higher order derivative terms of spatial derivatives and field strengths and so on, nothing that has a large mass. So what I've done is, again in our EFT language, we have another large parameter, that's A times M. We have another scale. So I've made the scale dependence explicit, right? Well, this is trouble. Why is this trouble? What's wrong with this? We're not matching to QCD anymore. This is not the QCD Lagrangian. The leading order term is not QCD. Of course, we now also explicitly see how it deviates from QCD. This doesn't matter, but if M1 over M2 is not equal to 1, I have the wrong kinetic term, which is just another way of saying I have the wrong kinetic term, but it's now explicit also in this. So what it means that if I just do the matching the way I've always done it, the straightforward semantic way, I screw up. It's the semantic matching that doesn't work anymore. The solution is already obvious. Instead of matching this, my improved Wilson action, straightforwardly trying to match it to QCD, I can match it first to QED and then have different matching to QED. What did I say QED for? HQET, and where I can take care of this mismatch right away, tune the kinetic term correctly, and the continuum QCD Lagrangian is also matched to HQET, and it all works out. The other thing I can do is, what is wrong here is that the spatial derivative and the time derivative terms are now mismatched.
It's an anisotropy.
It's an isotropy. So I can introduce an isotropy parameter, and that was also our first solution in our formulation of the Fermilab approach. So you write down the Wilson lattice action instead of keeping the time-like and space-like derivatives with the same coefficient. You allow for the space-like derivative to have a different coefficient from the time-like derivative, and you carry that out to all higher orders. Then you adjust the symmetry parameter so that this is exactly 1. Again, you can do this at all orders, at any order in your calculation. You can do this perturbatively, tree level 1 loop, or to non-perturbatively. So you introduce an isotropy parameter, and now you're back in business. And this approach is still used by the RBC collaboration. They are using Wilson-like heavy quarks with an isotropy parameter and also a non-perturbatively tuned Clover coefficient in order to have heavy quarks that are at tree level completely order A improved. Okay, so there's more to the story that I didn't get to, and I will finish up a speedy discussion of this at the beginning of lecture 3. But meanwhile, there's lots of exercises that are in the notes that I'll drop that you'll have access to this afternoon if you so desire. I think it's exactly 12:30, so let's stop.